Oh,
You're good to go.
all right.
I'm just checking my. Ready.
All good.
All good.
All good. All good. Good afternoon. Good morning. Good evening to wherever you are at this point. We want to say welcome to Quantum Thursdays, hosted by Co-Design Center for Quantum Advantage, or C2QA. I will be your moderator today, and my name is Kimberly McGuire. I am the Chief Operations Officer for the C2QA Center, one of the 5 Department of Energy Office of Science quantum centers that has endeavored to enter the space of understanding and solving challenges in quantum information science. I am so honored and pleased to welcome Sam Stein today, who will be presenting his story and his results and research on qubit, which is quantum Bayesian error mitigation over the Hamming spectrum for quantum error mitigation. So before Sam goes into some of these details, we just want to take this opportunity to welcome him. Welcome, Sam.
Hi, thank you for having me for this.
Thank you, and so glad that you're able to spend the next hour with us. Many of you may have already read all about Sam on the advertisements that have gone out, but they don't always tell the full story. So what we're going to do today is Sam is going to not only share his research that he's currently working on for C2QA, but he's also going to share a bit about his journey and how he came to the place that he's in today from a personal as well as a professional and career pathway. So Sam, we're going to open up this Quantum Thursdays just for a bit with something that I call rapid fire quantum questions. And what that really is all about is just trying to, get to know you a little bit better. So I'm going to ask you a series of questions, and you, Sam, will respond with the responses that make the most sense, but you only have 60 seconds to answer all of the questions. So are you ready?
All right, sounds good.
All right, Sam, here we go. 60 seconds on the clock, and it goes now. Sam, who is the comic book character that you most align with and why?
This is all right. Probably Thor. I like Thor. He's cool.
Okay. What is the most interesting thing about a qubit that you can relate to your life?
Jesus, these are so probably they're a mess. Probably that.
They're a mess. Okay. Sam, what has been your greatest accomplishment to date and why?
Probably presenting, joining quantum information sciences, and then presenting my work for best paper at the International Symposium on Computer Architecture within 1 year of joining the field. I was really proud of that.
That's pretty awesome, Sam, I gotta say. What's the favorite place in the world that you've ever lived in?
My home, South Africa.
South Africa. And Sam, who was your mentor?
My mentor? This guy, Gary Weiss, Fordham University. I just moved to America. I didn't know anyone, and he just took me in, put me in a research group. We published a few papers, and he just kind of guided me into the world of information, of like data science, data analytics, machine learning. I'd never joined it. I didn't know what I was doing, and we had like weekly meetings, and it was really valuable. Like that guy from Fordham, he's a great guy.
Oh, we love that, Sam. So I think those 60 seconds gave us a little bit more insight about who you are as a person. And thank you for accommodating my quirky style of moderating. So at this time, we just want to remind us of a few of the rules, if you will, guiding this lecture. We are asking you, if you're not speaking, to please be on mute. We welcome you to turn your cameras on. If you have a question, please be sure to put them in the chat window. If you would like to ask the question on camera, I'm sure Sam will oblige. And at the very end of our presentation, we want to see those smiles and those beautiful white teeth. So if you wouldn't mind, please turn your cameras on, and we will take a snapshot of all the beautiful faces that we see who have joined today's session. So Sam, without further ado, the floor is yours.
Alrighty. Hi, everyone. I hope everyone can hear me. I'm going to guess they can. And so I'm going to present my work today. We did a Pacific Northwest National Lab under C2QA. As I said, it's QBEEP. It's a quantum Bayesian error mitigation over the Hamming spectrum for quantum Bayesian error. Yeah, wow, I say error mitigation twice. I should probably change that. Error mitigation over the Hamming spectrum for quantum error mitigation. And this is just an algorithm that we developed based on some empirical observations on quantum computers to try and mitigate errors using just a structure that we observed. So before I get into like the science and before I get into all that, I think that it's good to just give some, as Kimberly said, like just give some background as to who I am, my journey to quantum information sciences and how I work at PNNL and all that, because I mentioned South Africa. So my journey started when I graduated from high school and I joined University of Cape Town, which is an amazing university in South Africa. So on the bottom left, it's really beautiful. It's on a mountain, had to hike every single day. And yeah, so I did my undergraduate in chemical engineering. So that's like grounding myself in science. It was really hard. I failed a lot of courses. It was really, really challenging. I went to some boot camps, it's true, but we made it. I graduated cum laude eventually, and in 4 years, and I was pretty proud of that. And then realized I don't know why I didn't do computer science and all that stuff, but it doesn't actually matter. If you just do anything in science, you can kind of pivot into any other science mostly. And then decided to move to America for data science, where I joined Fordham University in New York. And in this time, I joined a bunch of research groups. Got really passionate about data science, machine learning, all those kinds of things. And what's really, I think, interesting and important about my time that I observed at Fordham was I wasn't the courses were very generic and very trying to train anyone, from accounting, from communications, all in the talent of machine learning and stuff. And that's really hard to do. So because of that, the level was quite below what I did in ChemEng. But in the time at Fordham University, as I mentioned, Gary Weiss, I reached out to professors and I found people that were in my domain and things that I were interested in, and I asked them to join their research groups, and they let me join their research groups. And that's really what drove me, gave me infinite value out of my education. And then I got an email saying, you should read this book on quantum information sciences, and I read it. And then I wrote a few papers with a guy called Dr. Mao, who was working with Dr. Ang Lee at PNNL, and then eventually got this position after wrote some papers at Fordham, wrote my master's thesis on it, graduated, joined Pacific Northwest National Lab, and I've been under C2QA ever since, published a bunch of papers, and this one is one of our most recent. It's pretty interesting. I think it's pretty cool. It's a pretty neat observation. And yeah, it's under review right now. Hopefully it gets in. It'll get in. So yeah. So I don't know how much a lot of the audience know about how we structure quantum, because a lot of people know about devices. We know about qubits, transmons and all that stuff, but we don't know how it looks when we submit a circuit and how when we actually run an algorithm for quantum computing on an actual quantum computer. And one of the ways that we deal with it, especially under superconducting quantum computers, is gate-based computation, where you have a set of qubits, which is very similar to how bits are. You might here on the left in this quantum circuit, we have 3 qubits, Q0 through Q2, and you apply operations that just manipulate that quantum bit. So for example, under Q0, we have a Hadamard gate, which just puts it into a superposition. And you don't really need to know that much about what's exactly happening in this circuit, but what you can just appreciate and see in this circuit is you're transforming your data by time, and then you're measuring it. And I imagine that we all kind of we're aware that you transform your quantum state, you evolve it according to time, and then you observe it. And that observation is going to be one discrete bit string. That one discrete bit string that is with the probabilities of observation according to how you prepared it. And so that's how we prepare these algorithms and these circuits. And then we also have access to the processes that actually do this, which have the quantum bits, the qubits on them. So on the right here, we have I think that's IBM Lima, and it's a 5-qubit superconducting quantum processor. So 0, 1, 2, 3, 4 represent 5 qubits that are all they're real. They're 5 superconducting qubits, and they're on a chip. And so what's important to realize here is 0 and 1 are two qubits that are physically connected, and 1 and 2 are physically connected, and 1 and 3 are physically connected, and 3 and 4. And so what you do is you get these ideal quantum circuits that you build, these algorithms with these tasks that you want to accomplish, and you put them onto these processes, and you transpile them. And so you move qubits onto physical qubits, and you do some optimization process such that you can actually run this algorithm. But so now we have this idea of how we have an algorithm, we have a processor, we can run things. You know, we have 127 qubit processes. If things were all ideal, we'd be golden. We'd be able to do a whole bunch on that processor. But unfortunately, there's a lot of things that challenge near-time quantum computing, such as specifically its noise. It's running near-term algorithms that we compound countless errors in lots of different forms into our algorithms, such as just the time it takes to run the algorithm, the fidelity of gates. And the fidelity of gates you can kind of just think as maybe like the probability of applying the gate correctly. So for example, a 99% fidelity might have like a 99% chance of correct application. And that like chance is kind of going to link into this paper, into like the observation of the structure of errors. And so what's holding us back really is noise. And that's why, I mean, right, we're in the noisy intermediate scale quantum era. So what we have on the left here of that algorithm that we had demonstrated with that circuit is, in the ideal world, we're just observing two bit strings. It's 0, 0, 0 and 1, 1, 1. And they each have a probability pretty close to 50%. This is from sampling, so there's going to be some deviation from it. But then what we have on real processes, when we submit these to real things, is we observe that there's going to be a whole bunch of other outputs that aren't actually correct, but they're corrupted outputs from noise. So what we see on the right here is there's another 6 bit strings that we observe that aren't actually real. They're not real results from the algorithm. They're corrupted results. For example, 100 we would say has a 3.9% chance of being observed, yet it wasn't actually a target output from the algorithm. And so noise prevents us from actually attaining an advantage. It prevents us from attaining an advantage. And so tackling it through things such as quantum error correction and quantum error mitigation are really important. Speaking of quantum error mitigation, there's a really recent, so quantum error mitigation refers to it's a technique where you try to reduce the errors that occur in quantum computing algorithms via post-processing techniques and other. It's not live, it's not during the computation. So actually what's really interesting is that IBM posted a blog very recently saying that quantum error mitigation is the goal, that is the path that takes us from NISQ to an actual quantum computing useful world. And this is very promising for especially this research, because we're trying to evolve that field and look at error mitigation techniques. And all error mitigation techniques really are trying to do is find structure within these errors. So now that we've set the scene, computers exist, they're noisy, they make errors, that's a problem, but we want to reduce those errors as best we can. And how can we reduce those errors? So quick diversion into the Hamming spectrum. The Hamming distance is a really important notion for our paper to understand. And the Hamming distance is the difference between two strings by discrete distances, differences between the two equal length strings. And what this means is, for example, if you have a bit string of 101 and 100, it has a distance of 1. And the reason that is 1 and 1 are the same, 0 and 0 are the same, 1 and 0 are not the same, so that adds 1 to the distance. And I have examples in the bottom left where H just means Hamming. And this represents how you might compute the difference between two strings in the Hamming spectrum. And it's really useful because it provides a distance, right? Like now we have a distance between two strings based on their binary 1 and 0. And if you think about it, all the outputs of quantum computers are just bit strings. So we can have this notion of distance between bit strings on quantum computers, such as if you have an output of 000 and 001, their Hamming distance is 1. And if you have an output of 000 and 111, their Hamming distance is 3. And that's the most distance that you can have in that system. And yeah, so exactly what I just said is that every observation has a Hamming distance with every other observation that we have. And so you can get this like kind of graph structure on the right here. And so what would be really interesting is if there's a structure in this, if there is a Hamming structure within these errors, because that would be an underlying structure that we could exploit to try and mitigate. And so there was this paper this year in ASPLOS that was extremely interesting called Hammer. And Hammer looked into this Hamming structure of quantum errors. And what it said is if there is an expected Hamming distance, so the average distance between two bit strings is just equal to half the number of qubits, then you have no structure. And that makes sense, right? Like if you have a random state, like for example, heads and tails, which is 1 and 0, the average Hamming distance is going to be half because you're going to get 50% 1, 50% 0. The distance is going to be 0.5. But if you have it a less than half, then you know that there's locality because now suddenly they're clustering around some bit string. And so what they claim is that the expected Hamming distance is going to be less than half of the number of qubits that you have. And so what they go on to show is that that actually is the case. And that is, I think, an extremely interesting observation in that the majority of your errors that come out of an algorithm are going to be clustered around your correct result. And we can see this so to go through these, on the left, we have this 4 qubit output probability plot, where you're looking for the homogeneous 1-bit string, which means all ones. And what we observe is the probability of having an observation with only one failure is much greater than the expected Hamming distance with uniform errors. And then this probability distribution drops. And what this shows kind of is that like the likelihood of having multiple Hamming errors goes down and down as you increase the Hamming errors. And on the right here, they do comprehensive evaluation over a whole bunch of algorithms that we don't really need to get into. But what it shows is this black line in the middle shows an average, the uniform error rate, which would just be like random. And it shows that the Hamming distance between the correct key and the incorrect key has structure, and it has structure. And that's just seen by the fact that the average probability of the Hamming bin is above it, and it's statistically significant. And it's this kind of what the whole paper does is it takes this observation of they're clustered, generates a probabilistic reclassifier, which we see here, and it generates an error mitigation technique based on this. And so what it does is it looks at the output of a quantum routine, it looks at the structure of the bit strings that it receives, that it sees, and it then has a weighting function, which we see here, where weight is equal to 1 over f, and it will try to reconstruct the correct output. So this is really interesting, the fact that you can just get free fidelity boosts based on this observation. They show substantial fidelity boosts on a bunch of different algorithms. And what's crazy is like they just take this weight of 1 over f, where f is the distance to the correct solution, or the solution, and they apply this update, and the fidelity of a bunch of algorithms goes up substantially, right? They show this on Bernstein Vazirani and like lots of other algorithms, but we don't really need to get too much into their paper, but we can just kind of accept and say that was really cool. That was really interesting that they wrote this paper and they found the structure within the Hamming spectrum, and then they used this Hamming spectrum structure to regenerate and improve results of their of past run algorithms. And what's also crazy is like some of this stuff, like you can take algorithms that have run 2 years ago and you can do this analytical model on them where you try to reconstruct its Hamming spectrum, and then with that you can boost their fidelity. So now I feel like I've just said a ton of words, and we've gone through like there's Hamming spectrum, there's errors, and there's all this stuff, and there's all this reconstruction, and that kind of sets the scene for the motivation and the observation and the drive for this paper. But before I go into QBeep's structure and what it contributes, I want to ask, is there any questions? Because I feel like I've probably lost around 60% of you, and we can try and get you back on track, but that requires you to ask questions. And I'm completely expecting pure silence here.
Hey, Sam, I have a question.
Hi, David. How's it going?
Hey, for this hammer technique, so this you need to know the answer, I guess.
They just use the so in their paper they just use the outputs probability in their reclassification thing. They don't know the output. They just look at the probability. Everything will get corrected under the assumption that it is the correct solution. So they'll just use the probability of an observation to reconstruct it. And what happens is, because the probability of like, for example, this 11001111 is really far from another Hamming spectrum that's close to the homogeneous 1-bit string, it has a really low weight. So it doesn't really contribute to any of that reconstruction. But the homogeneous 1-bit string has a large population around it, which causes it to have a lot of contributions towards its like boosting. But we tackle that in our paper on qubit, where you just everything is assumed to be, you assume that what you're observing is an unbiased estimator of your actual probability. And because of this like inherent nature that like more correct results will be more clustered with more correct results will be more clustered with like errors around it. Naturally, there's more connections and more reclassification flowing into that, which will make sense because we use a Bayesian network to update our states. So you don't need to know the true correct solution.
So could I think of this method as like sort of you make a histogram of the shots that came out of the experiment, and you're finding kind of the mean of that histogram and saying that that's, but you make the histogram in a certain way based on the Hamming weight.
Yeah, it has in like if you have like this histogram of like Hamming spectrum and look, you find the mean, but mean by definition of like Hamming distance.
Okay.
Which they and then the distance to a bar will be a function of its distance. But that's one of the complaints that we think, like, this paper is really interesting that it observes the structure, but the 1/f weighting function is like not that good. It can't capture all complexity, right? You can't have different circuits like BV on 4 qubits versus QFT on 10 have the same weighting function, have the same function describing their error structure. So
Thanks.
yeah. So we're good to go. It's qubit. Okay, we're gonna move on. So now, any more questions before we move on? Nope. Okay, cool. So now, based on this, now we've set the scene. We know what exists in this like Hamming spectral error mitigation domain. And so what we try to do is we try to look further into it and kind of use it as a motivating work to look at like what actually structure exists within this Hamming spectrum and how complex is it? How can we model it? What can we do to exploit it further? And how can we boost fidelities even more? So we know Hamming structure exists, but they only use 1/f, which indicates that there is a strong sense of locality to their errors, in that the closest bit string Hamming spectral error, for example, 111 to 110, will be the majority error. It will be one distance, and then the second majority will be 2 and 3 and 4. And we observe that that's not the case. So over here we have a pretty janky plot that we just like toyed around with. I've been toying around with the last few days trying to do analytics. But so if you take a 12-qubit randomized benchmark, you know your output's supposed to be the homogeneous 0-bit string. For this, we mixed in a bunch of benchmarks that have like target bit strings of like 110011, like random state preparations. And then on the y-axis, we have expected Hamming distance. And if you remember back from the Hammer paper, anything with an expected Hamming distance of n/2, and in this case it's 12, so 6, is going to be like it's destroyed. Like you're just observing random errors in your system. And so what they observed is what they claim that there's no structure there. Where they show is the local structure, where your expected Hamming distance is low and it's clustered around your dominant output. But they left this large amount of information on the table between the two, where you have non-localized clustered errors, which is what qubit really tries to exploit. In that you don't have, the errors are not clustered around the true solution, but there is going to be a large cluster of errors some distance away from the true solution. And the way we visualize this is like, if you have this 111 1-bit string, right? They show that like, one failure is going to be most probabilistic, then 2 failures, then 3. What we observe in our experiments is that this is not the case all the time. For some complexity of circuits, you have like clusters around 3 Hamming distance away, and you can exploit that to try and correct for your errors. So they use the model of 1/f, but we argue that the Hamming structure varies as a function of your circuit, as a function of your backend, as a function of like the quantum processor, the time, how recently calibrated, all that stuff, all the features that describe how well your processor is going to perform. And so kind of the features that we really zone in on are that your gate fidelity, which is like circuits are comprised of gates, right? And those operations have fidelities, and those fidelities are bound between 0 and 1. And then you have decoherence and spin-spin relaxation, and just and these are your T1 and T2 times. They're like your lifespan of information in your quantum system. And we know that's also we model that as an exponential decay, and that's also between 0 and 1, the probability of a decay happening. And so we really zone in on these two things because these two things are functions of both the transpilation. When you have a circuit and it's moved onto a physical system, your gate counts will be according to the physical system structure. Your time, the total time of the circuit is going to be a function of the system. And your circuit structure, like your number of gates, is a function of the algorithm that you're running on the processor. So higher complexity algorithms a failure event, and that like a 99% fidelity, for example, indicates a 1% failure event.